Hi everyone, my name is Zhenrong and I'm a third-year PhD student at UCLA, working with Professor Tony Nowatzki. Today I'm excited to share our work, Stream Floating, Enabling Proactive and Decentralized Cache Optimizations. As multi-core CPUs continue to scale up, the cache system and on-chip network have become increasingly important bottlenecks. Consider a multi-core system with mesh topology, and the simple programming summing up an array A. Conventionally, the interface between the requesting core and the remote cache is based on simple request and response messages. A consistent challenge is that the cache is oblivious to the program behaviors such as the access pattern, reuse distance, etc. And over the last few decades, architects tackled these problems with microarchitecture-only innovations for prefetching, bypassing, replacement, and coherence. However, even for well-structured multi-threaded programs, such a reactive cache system is far from optimal. Over the 12 multi-threaded data processing workloads we studied, 72% of cache lines evicted from the private L2 cache have no reuse, which not only causes thrashing in the private cache, but also introduces up to 30% extra network traffic for request and coherence messages. Our idea is to bridge the information gap between the cores and the caches by encoding well-defined patterns of memory access directly into the ISA as first-class primitives called streams. For example, here this linear access to array A can be represented as a linear stream, which enables accurate prefetching in the hardware as the pattern is well-defined. However, streams not only just define a sequence of memory access, but also contain much higher-level information like the access pattern, reuse distance, etc. Such information is more accurate, as the compiler has access to the high-level program structure, and the cache is trying to recover exactly the same information, which inspires us to directly offload the stream pattern to the cache and build a proactive cache system. Specifically in this work, we explore the idea of exposing streams to the cache and introduce three major optimizations. The first case is the A5 access pattern like A of I. Instead of sending individual requests to specific cache lines, the core sends one request for the entire stream pattern with little reuse, and the cache can run ahead of the core to stream back data. This effectively allows streams to run in the remote L3 banks, and we refer to it as stream floating, which reduces the request traffic and lowers the latency. Another interesting case is for indirect access patterns like B of A of I. A traditional system has a long dependence chain to first get array A and then array B, while stream floating can be helpful as it enables decentralized address generation. Now the cache can directly issue indirect requests on behalf of the core. This also reduces request traffic as well as the data traffic, as we only need to transfer the required subline data. Finally, in well-structured programs, the cores may request the same data, but the cache suffers from redundant requests and response traffic. Streams define long-term behaviors with a few parameters, and a simple pattern matching is sufficient to detect the same request pattern from different cores, enabling the cache to multicast the response and further reduces the network traffic. We call this stream confluence. Overall, streams enable proactive and decentralized cache optimizations with lower latency and less thrashing. As for implementation, here is a simple program that sums over indirect access B of A of I. In the stream ISA, streams are configured before entering the loop and managed with special load and step instructions. In the microarchitecture, we added stream engines to the core, the private L2 cache, and the shared L3 cache. The core stream engine determines if a stream is suitable for offloading by combining compiler analysis and dynamic history information, such as hit rate in the private cache, etc. It offloads the entire stream pattern to the remote L3 stream engine, which proactively transfers stream data back to the core. Stream data is not cached, and we extended the messy protocol with a special get uncached request to bypass the coherence protocol. As streams advance, they automatically migrate to the next bank and keep streaming until no credits or released by a stream end message. Floating streams can be integrated into both weak and strong consistence models with our proposed aliasing detection scheme. To complete this example, the L3 stream engine can also issue indirect requests on behalf of the core, achieving decentralized address generation. We evaluate stream floating by extending the LVM compiler and the Gen5 simulator. Here is the network traffic breakdown. We count the number of traveled hops for the control and the data messages. We also count the overhead of all the messages to manage offloaded streams, such as configure and end messages. We can see that the hardware prefetcher actually increases the network traffic by 33% due to aggressive prefetching. The next configuration only offloads A5 streams, and this reduces the overall traffic by 30%. Most of the reduction comes from control traffic, as we offloaded the whole access pattern at once and bypass coherence protocol. Some benchmarks also see reductions in data traffic, as not caching stream data improves the hit rate in the private cache. Also, it only introduces about 2% traffic overhead to control offloaded streams. Enabling indirect streams and stream confluence further reduces the traffic for certain benchmarks, yielding on average 36% of traffic reduction and about 39% of speed up. To summarize, we explore the idea of embedding streams in the ISA and directly offload it to the cache. This bridges the information gap between the core and the cache, enabling proactive and decentralized cache optimizations. More importantly, as the number of cores increase, it is time to explore rich semantic information in the ISA and use it to improve the memory hierarchy. Thanks.